All right, question 16 is up next. Silver will tarnish over time as it's exposed to hydrogen sulfide and oxygen. So silver, hydrogen sulfide, oxygen, we form silver sulfide and water. What is the oxidation half reaction? So again, we can kind of go through the same process of assigning. I gave you plenty of opportunities to practice redox reactions in this. So yeah, any pure elemental solid, right, is zero. Any diatomic, also zero. Hydrogen sulfide, even though it's a gas, we can assign oxidation states to see if any of the charges change. So hydrogen sulfide, I've got two hydrogens at +1, and sulfide would be -2. That's neutral. We can split up silver sulfide as well, Ag2S, right? We'll see the same thing. Well, let's just say we don't know silver because it is a transition metal. Sulfide is always -2. The whole thing has to be 0. So that means I have to have 2 plus from the silver. Each silver is +1 each. And then for the water, we've split up water a few times today. Two hydrogens at +1 each. Oxygen's -2. The whole thing is neutral. So again, we can see that hydrogen does not change. But what changes is our silver. Our silver goes from 0 to +1. Oxygen goes from 0 to -2 in the water. So we'll write those two half reactions, balance them out. Hopefully this helps Ethan, or yeah, I think it was Ethan, right? Yeah, write the half reactions. So here's one half reaction. Silver, 0 goes to silver +1. How does it do that, right? It has to lose an electron. And I guess to balance this out, say I've got 4 silver zeros, go to 4 silver +1s. They each lose 1 electron, so 4 electrons, right? That is oxidation. Oxygen, I've got 2 oxygens that are 0. I'm going to end up with 2 oxides at -2 each. I need to have the charge on both sides of the equation balance out. So right now I'm 0 here, I'm -4 here. The only thing I can add in would be negatively charged electrons. So for this to balance out, all right, the 4 electrons that I lost here, I can balance those, I can gain those, right? Oxygen gains those electrons that silver lost. Reduction is the gain of electrons, right? Can you reduce it by 4, or does it change the equation? We could reduce the silver equation by 4. The reason why I wrote the whole equation out was it would have been a little bit confusing if I just had 1 silver going to 1 silver and 1 electron, and then all of a sudden I need 4 electrons down here. So I used the full equation right here just so that we could see in total I'm losing 4 electrons. In total I'm gaining 4 electrons, right? So the oxidation half reaction, right, would be this reaction right here with silver. Silver losing those electrons. And then yes, for the final answer for the oxidation half reaction, yeah, we could reduce that and just say, yeah, silver loses 1 electron each. It looks like I didn't do that, but that would have been fine. All right, so there's choice B. All right, for 16, 18, 19, and 20 are up next. Right, which of the following conditions would always result in an increase in internal energy? So the equation that we talked about for energy, right? Delta E equals Q plus W, right? Heat and work. We're looking for an increase in internal energy. So increase, system gains heat, that's a plus Q, but it does work. So that's a minus W. So that one, we're not sure. It depends on the magnitude of each of those. System loses heat, minus Q, has work done on it, that's a plus W. System gains heat, that's a plus Q, and has work done on it, that's a plus W. So yes, in this case, we would always have a positive delta E because we're going to have a positive Q and a positive W for that reaction. We gain heat, which is positive Q, and the surroundings are going to do work on the system. That's a positive W. So for 18, choice C is the correct answer. All right, question 19, Hess's law. Got these two reactions, A going to 2B, A going to C, delta H for both of those. We're asked about this reaction though. The energy for 2B going to C. So what we need to do is somehow manipulate these two reactions so they add together and give me the reaction that I'm looking for. So it's pretty easy to see I need 2B as a reactant. So we're going to flip this reaction, flipping this reaction, 2B going to A. We flip the delta H would be a negative 456.7. Because here I went uphill, right? The opposite reaction would be downhill. And then A going to C, I add these two reactions together. Oops, I need our delta H as well. That's minus 22.1. Add our reactions together, add our delta H's together, right? 2B goes to C, and then the delta H for this overall reaction, minus 478.8. Yeah, choice D for question 19. All right, question 20. Can someone toss the molar mass of sodium chloride in the chat for me? Thank you. All right, we're going to go from grams to moles and then moles to energy using our thermochemical equation. So got 75 grams of sodium chloride. And to go from grams to moles, I need my molar mass. That's what I asked for. And then we would need our thermochemical equation for the next step. So yeah, we're going to start with 72.5 grams of NaCl. The molar mass is 58.44 grams in 1 mole. Wow, question 20 is the first time I had to break out the calculator. Well, second time I broke up the calculator. 72.5 divided by 58.44. And I've got 1.24 moles of NaCl. That's step 1. All right, step 2, we've got to link moles to energy. For that, I need the thermochemical equation, which tells me for every 2 moles of sodium chloride made, I'm going to release 411 kilojoules of energy. So 2 moles of NaCl and 411 kilojoules of energy. We've got less than 2 moles, so we should have less than 400 kilojoules of energy being released. So multiply that by 411. And I get something like 255 kilojoules of energy would be released in this reaction. So choice C, right? Mass to moles using our molar mass, and then moles to energy using our thermochemical equation right here, using the coefficient that for every 2 moles out, this is the energy out. Well, I don't have 2 moles, so I'm going to have less energy, right? And we see that here, minus 255 kilojoules of energy released in that reaction. All right, I'll stop the recording here.